All right, hello grade 12s. We are kicking things off with probability, unit 6. Before you actually start this video, you should have watched this video already. Gives you a general rundown, a little bit of a review from probability, because you wouldn't have seen probability likely since like junior high. So please make sure you watch that first, so that we can roll into this a little bit more smoothly. Now, probability exists everywhere. There's applications in all areas of our lives, whether these applications are in medicine, insurance, statistical physics, law, decision-making in business, gambling, you name it, statistics are often involved, which is kind of cool because there's not a lot of times where one topic in a subject branches off to so many different areas in our lives, but statistics and probability is one of them. Now, probability is a value that tells us how likely an event is to occur. So that probability can be represented in many different ways. It can be represented as a fraction. It could be represented as a decimal. It could be represented as a percentage. But all of those have a similar meaning. Now, there's different probabilities that exist, but probabilities are limited. So we can see on the probability line below that probabilities can range as low as 0 or 0%, depending if we're talking about fraction/decimal land or percentage land here, all the way to 100% if we're talking about percentage, or just 1 if we're talking about fractions or decimals, and can be anywhere from absolutely impossible, like this thing cannot happen, there is absolutely no chance, to it is a 100% certain thing that it will happen. There is no wiggle room, there's no room for it not taking place. And it can be anywhere in between. Now, there's certain types of probabilities that have special names. So we can see that on the probability line that's drawn. But let's name those out as well. So first and foremost, there's something called an impossible event. Now, an impossible event is just an event with a probability of 0. Or if we're talking in percentages, 0% chance. Which means it'll never happen. So if I have a 6-sided die and I'm going to roll it and like, ooh, come on, lucky roll here, it is impossible for me to roll the number 7. Because there are only 6 numbers on that die, and it is only the numbers 1, 2, 3, 4, 5, and 6. So there's a 0% chance it is an impossible event. There is also something called an equally likely event. An equally likely event is an event with a probability of 0.5 or 1/2 or 50%, again, depending on how we're representing that probability, which means there's an equal amount or an equal chance that it will happen versus not happen. So for an example, if I flip a coin and I'm trying to land on a heads, I have an equal chance for this coin to land on a heads as I do for the coin to not land on a heads, aka to land on a tails. If I'm rolling a die, I have an equal percent chance of getting an even number as I do of getting an odd number, right? So those are equally likely events. The last type of an event that has a special name is called a certain event. I realized I did not write the word event after all of these, but I'm going to throw that in. So a certain event is an event with a probability of 1 or 100%, meaning it will always happen. So if I roll that same 6-sided dice, but now I'm like, hey, I really want to roll a number less than 7. Yeah, I'm going to do it. It's going to happen. Every single time it will happen. 100% chance. Now, when I'm looking at that probability line, I will notice that if I'm talking about probabilities either in decimal or fraction form, that probability will range between 0 and 1. I cannot have a probability of 1.5. I cannot have a probability that's negative. If I've converted those decimals to percentages, which means I'm simply timesing them by 100%, that means I can get between 0% and 100% as a probability. I cannot get higher than 100%. There's not like a 500% chance that we're going to do math the next time you see me. No, it has to be between 0 and 100. And if I'm representing that as percentages, I need to have the percent sign because I know a percent of 100 if it is not, I know a probability of 100 if it's not representing a percentage is not possible because 100 is greater than 1. The only time I can have a probability of 100 is if I am talking about a percentage, which means I need to have that percent unit there. Now I'm able to calculate probability, and here's the formula that exists. So anytime I have this capital P in front of a set of brackets, that implies the probability of whatever's inside of it. And typically, we use a capital E because E can represent the probability of an event. But I can put any letter I want in there. So I can put the probability of A, or the probability of Q, or the probability of S. I kind of have options here. But that just denotes the probability of some event occurring. Now, it's calculated by saying, okay, what number of outcomes exist that would give me a favorable result? So if I'm talking about what's the probability of rolling an even number on a 6-sided die? Well, I'm looking for the number of even numbers on a 6-sided die to be my numerator. And when I'm talking about the lower, that denominator of my fraction, the lower part of my fraction, that's just the total number of possible outcomes. So we use a capital N to denote that. It's kind of like the number of elements in my universal set or the number of elements in my sample space, the number of elements that are actually possible to take place. And we just use a capital N to denote that. Okay, we're going to go through a couple of basic examples. And then we are going to do 5 things. Thing number 1, we are going to identify a list of all of those possible outcomes. Then we're going to calculate capital N, which is the number of possible outcomes. And by calculate, I mean count. Okay? Then we're going to list the set of all of the favorable outcomes. And then we're going to count the number of outcomes that are actually favorable. And then we're going to determine the probability. When we do this probability, we are going to represent it as a fraction, a decimal, and a percentage. And remember, if I'm going decimal or percentage here, I have to do it to 2 decimal places. Always, always, unless otherwise stated. Okay, so first things first. My example of getting a tail when flipping a coin. So when I flip a coin, here are all of my possible options. I can land on a head, or I can land on a tail. That's my set of all possible outcomes, or my universal set. My capital N, the number of elements in that set, is 2. Now the set of favorable outcomes is the set that's just straight up tails, which means my number of elements that are favorable is 1. And I can turn that into a probability by saying my N of E, which is 1, over N, which is 2, gives me a half. Now, we could do this without using our calculators, or should be able to do this without using our calculators, and I get 0.5 or 50% chance. Now, all those 3 answers of my probability of getting a tails represents the exact same thing. So unless it tells you to specify, you do not have to put all 3. But this question told us to put all 3. So here we are. All right. Next, rolling a 5 with 1 6-sided dice. So my universal set, well, the possible outcomes, I can get a 1, a 2, a 3, a 4, a 5, or a 6. There are 6 possible outcomes that exist. Now, the ones that are favorable, the ones that will make my event come true, is just straight up if I get the number 5. Which means there is one possible outcome there. So my probability is 1 over 6. And if I beep boop bop that into my calculator and round to 2 decimal places, I get 0.17 as the decimal because I did have to do some rounding. But something I want to point out is even though I rounded to get that decimal answer, if I'm converting this to a percentage, I still need to have 2 accurate decimal places. So that decimal is technically 0.166666666 forever. So when I convert that to a percentage, i.e. times that by 100, I actually get 16.666666, etc. But I'm rounding to 2 decimal places. So my decimal and my percentage, even though like it's the same values just rounded or slightly different looking, I do need to make sure it's accurate to 2 decimal places based on the representation that I've chosen. So if I got to do this to a percentage, then I need to make sure those last 2 decimal places are accurately rounded to that percentage value. Something to point out. All right. Similar question, rolling a 7 with a 1 6-sided die. Okay, my sample space is the same. All of my possible outcomes exist as the same. There's 6 of them. But my favorable outcomes are an empty set. Remember that empty set notation from before? Or I can draw like a 0 with a slash through it. Which means my N of E, my number of favorable options or outcomes, are 0. Which makes my probability calculation quite nice. I either get 0 to 6, or 0, or 0%. This, if you remember, is called an impossible event. An event that has a 0% chance of taking place. All right, next. Randomly choosing a vowel, A, E, I, O, U, from a bag of letters of the alphabet. No, I'm not writing out all the letters, but as we talked about a couple units back, we can define our list in different ways. So I'm going to say the set of all letters in the alphabet. I don't have to define things by listing them. I can define them in words. That is okay. And hopefully you don't have to sing the alphabet to know there's 26 letters. Now the favorable outcomes, well, it says almost straight up in the statement there in the example, I only care about A, E, I, O, and U, which are 5 elements. I get 5 over 26, and I can figure out that decimal, I can figure out that percentage, and I get 0.19 as the decimal, or 19.23%. Please do the last one. Hopefully you paused, tried the last one, and you came back. Here we are. So if I want to roll an even number on a 20-sided die, my options are I can roll a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, or 20. If you rewrote that, rolling an even number on, or all numbers, sorry, let me try that again. If you wrote the set of all numbers from 1 to 20, great, fantastic. You should have gotten that there's 20 elements in that set. Now, the set of favorable outcomes is only the even one. So 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20, which there are 10 elements of, and I get 10 over 20. Now, yes, probabilities can be reduced and should be reduced. And on your calculator, if you hit the math button, it should give you option number 1 that says frac, which is short for fraction. I know this one you should be able to reduce in your head, but on a question, if we got something kind of crazy, you can always choose to use your calculator to help you reduce it. I get 0.5 or 50%. Okay, these are some nice, simple probabilities to get us started, but we are going to slowly start kicking things up a notch. And the nice thing about when we kick things up a notch is we actually have a lot of skills that can help us. So we've used strategies like Venn diagrams, tree diagrams, drawing tables of all of the possible outcomes like sample space tables. We've used the principle of inclusion and exclusion. We've created lists. And we can use a lot of those strategies to help us figure things out, which we use as kind of up to us, but something that we can use to help us out. Okay, in this first example, I want to consider flipping 3 coins, a penny, a nickel, and a dime, and I want to use a tree diagram to determine the probability of landing on 3 of the same sides. So either landing heads, 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 or tails, tails, tails. Okay, so my tree diagram, I have 3 different sets of branches. So I have my penny set of branches, I have my nickel set of branches, and I have my dime set of branches. Pause the video, draw a tree diagram. Okay, hopefully you've done that. So I've got a heads or tails for my penny. I've got heads or tails for my nickel. And I've got heads or tails for my dime. When I take a look at my probability, I can't just say P and leave my bracket empty. So I do have to define the event that I'm talking about. So I'm going to say E is landing on 3 of the same sides. So P of E is equal to N of E over capital N. Now the great thing is, my tree diagram, all of the end branches tell me, or the number of end branches tell me what my denominator is. So 1, 2, 3, 4, 5, 6, 7, 8. My denominator will be 8 in that probability. My numerator can be found by counting how many of those total branches from start to end will land in either, or end up in heads, 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 or tails, tails, tails. And I can do that. Here's heads, heads, then heads. No other branch will end up in heads, heads, heads. And so I'm going to go and say, well, is there a tails, tails, tails option? Yeah. There are a total of 2 branches that leads me to that desired outcome. And I could reduce that to 1/4. Now 1/4 is in fact my final answer. Now most of the times, honestly, probability leaves a fraction. Unless it tells you otherwise, do not bother converting. If you feel ever so inclined, you could convert. It is not incorrect. But it's just an unnecessary step if the question doesn't require you to do so. So just be advised. Okay, so that's how I can use a tree diagram to help me solve or figure out the answer to a probability question. Pretty cool. Next, a card is drawn from a standard deck of 52 cards. I want to find the probability that a card drawn is a jack or an ace. All right, I'm going to name this event. I notice that I have questions A, B, and C following. I'm going to name this first event A, I'll name the second event B, so on. So I'm going to say A is drawing a jack or an ace. Now when we take a look at this, hopefully you can picture a deck of cards in your head. A question like this, we can kind of think about either just counting all of the options that exist, right? Kind of like creating a mental list of all of the cards and just counting which ones are included that are a jack or an ace. I could also mentally picture or use the principle of inclusion or exclusion, where I'm talking about like the number that are jacks plus the number that are aces minus the number of them that are both, right? The overlap. And sometimes this can be really helpful. honestly, in this question here, hopefully you know that there's 4 jacks, there's 4 aces, and there's no cards that are both jacks and aces. So maybe not so super useful in this particular question, but might be helpful when we do have a situation where an overlap does exist. That way we can ensure we're not counting something twice. Now, when we take a look at this, the probability of A is the number of ways that I can get a jack or an ace. In this case, there's 8 jacks and aces, divided by the total number of cards. Well, if you didn't know, it says in the question there's 52 cards total. And I can reduce this. When I reduce that, that's 12 over 13. And that is a great answer. Yes, you can go ahead and convert this to a decimal or a percentage. Unnecessary. But if I do, 2 decimal places. Okay. Next one. I want to know the probability of drawing a 10 or a spade. So drawing a 10 or a spade. And this one I am going to use the principle of inclusion or exclusion, and I'm kind of doing this like in my head a little bit. So I know in a deck of cards there's 4 10s. I know a deck of cards there's 13 spades because 1/4 of the deck is the spades, or I could think of like ace through 10 and then jack, queen, king, 13 cards total. But in this case, there is one card that's both 10 and spades, so I need to make sure I'm subtracting that. So 4 plus 13 minus 1 is going to give me 16. So the probability of B will be 16 over 52, which does in fact reduce to 4 over 13. I'd like you to pause the video, try the last one on your own, and welcome back. So the last one I'm going to call event C, and that's going to be drawing a heart or face card. And again, I'm kind of using that principle of an inclusion and exclusion. I don't have to use it in like the formal sense here, but I'm using it to help me figure out that numerator. Now I know just like spades, there's 13 hearts. For face cards are the cards that actually have pictures of people's faces on them. So jack, queens, and kings. Now there's 3 face cards for every suit, and there's 4 suits. So there's a total of 12 face cards. But 3 of those face cards are also hearts. So I'm considering this, I'm going, okay, I have 13 hearts, 12 faces, 3 that are both. And that can help me figure out that I have a total of 22 cards that are heart or face, and then a denominator of 52, and reduces to 11 over 26. Now you might be thinking to yourself, okay, what if I don't want to use the principle of inclusion or exclusion? Like, what are my other options here? And quite honestly, you can think about this and literally draw them out of like, what are all of the hearts that I have? So I have ace of hearts, and 2 of hearts, and 3 of hearts, and 4 of hearts, and 5 of hearts, 6 of hearts, and 7 of hearts, 8 hearts, 9 hearts, 10 hearts, jack, hearts, queen, hearts, king, hearts, dear Lord. Okay. And then I can say, okay, well, add to that list all of the face cards. Well, I already got jack, queen, king of hearts. So jack, queen, king of diamonds, jack, queen, kings of clubs, and jack, queen, king of spades. And then I can go ahead and count them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oops. And that's how I got my numerator. Now, of course, drawing those out might take longer if you can like actually picture what's going on in the situation in your head, but always an option. Always, always, always an option should you want it. Okay. total probability rule. So since 1, or 100%, represents the highest possible probability, the sum of all probabilities for a given scenario will always equal 1. So when I take a look at this, think of like flipping a coin, because that's probably the simplest example that I can think about. Right? When I flip a coin, there's 2 outcomes. So the probability of landing on a heads is 0.5, or percentage-wise, 50%. The other outcome, the probability of flipping a coin and getting a tails, is 0.5, or again, 50%. Now, those are the 2 possible outcomes that can exist when I flip a coin. Nothing else can possibly happen, which means when I add up all of these probabilities, those probabilities, if they were decimal or fractions, will add to give me the number 1. But if it's listed as a percentage, it will add to give me 100%. Now, the thing that's kind of cool about that is if I'm down the road listing all of the probabilities of all of the different possible outcomes, I should be able to double check that my probabilities make sense by adding them together and seeing if I get either the number 1 or 100%. And if I do, probably on the right track here. The other thing that's kind of cool about that is if I know one of the probabilities and I'm trying to find the probability of the rest of it happening, well, I can just remove that from that 100%, remove that from that total of 1 being my probability there. So let's take an example here. Look at another example here. I'm thinking of a whole number between 1 and 10 inclusive. What is the probability that you guess the whole number I'm thinking of? Well, let's define something. So I'm going to say G here is that I guess, or you guess, the number I'm thinking of. Well, what's the probability of that? Well, the probability of G is, well, I'm thinking of a whole number, which means I'm thinking of one number. There's one number that I'm thinking of. And how many numbers exist from 1 and 10 inclusive? 10. So your probability is 1 in 10. Again, you could go into decimal land. You could also go into fraction land. And for this example, I'm actually going to write all of them in here, just so that we can talk about the next question. Now, what is the probability that you do not guess the number I'm thinking of? Now, just for the sake of starting to blend some of the notation we've talked about in the past, if G represents you guess the number I'm thinking of, let's say the complement of G is that you do not guess the number I'm thinking of. Now, the fun thing is I can figure out the probability of not G in a bunch of different ways. Way number 1 is the way we've always been doing something, is I can say, hey, look, let me look, okay, you're guessing one of the numbers, which means 9 of those existing 10 numbers are not correct, which means I have a 9 out of 10 chance of guessing it incorrectly, or 0.9 or 90%. Now, for this example, quite honestly, that number is very easy to calculate. The probability is not very complex. But why that's sometimes useful is because if that number was pretty complex to figure out, and it wasn't something I could count or easily figure mathematically, I can also just say, hey, look, the probability of not G is equal to 1 minus the probability of G, or 1 minus 1/10, which I can keep on going and say that's 10 over 10 minus 1 over 10, which is 9/10. Now, again, you might be looking at this and go, Miss T, that's harder. What are you talking about? That's way more complex. I promise you that this skill, this thought, is going to be really useful, and you're going to be thanking me about it, even though it seems more complex right now, when we get to more challenging situations. Okay, really useful point. Okay, last question. We're talking about a Venn diagram here. Now, in this Venn diagram, it's a triple Venn diagram, very exciting. And quite honestly, when we talk about that provincial exam, very frequently there's a triple Venn diagram on it. And actually, every single Venn diagram I've ever given you, I can ask you a probability-based question to follow it. Okay? So now that we're Venn diagram masters, we can tack on this added skill. So first and foremost, before I figure out the probability of anything in this Venn diagram, I need to know the number of elements in my sample set space or the number of elements in my universal set. And I find that just by adding up every single number, right? Every single area here, when I add them up all together, that'll get me my denominator of every probability that I'm about to do. And that denominator, can you add it up for me? I end up with n is equal to 320. So we're about to calculate a bunch of probabilities here. All of the denominators will be 320, at least before we reduce it. Because we're talking about the same Venn diagram, which means it still has the same number of elements in the universal set, or in the sample space, or the total possible outcomes, whatever context we're talking about here. So when I talk about P of A, I'm going to have something over 320. Now that something is N of A. And I can tell you that you spent a lot of time calculating what N of A is in previous units, and I can do that here again. N of A I can find by just adding those numbers in my A circle together. And we end up with 110 over 320. And of course, if I reduce that, I get a probability of 11 over 32. All right, these last three examples, they look a little bit different, but P of an event is the same as translating to the probability of an event taking place, the probability of, or P of C. So don't get freaked out that the questions look different. It's just representing it using either notation or using words. I'd like you to pause the video and get that final last three set of answers. Go. Welcome back. Okay, P of C. So I'm adding all of the numbers up together in C, and I am getting 105 over 320, which reduces to 21 over 64. And again, I am welcome to convert to decimal. I am welcome to convert to percentage, but it is unnecessary. Next, I have the probability of B and C. It's the intersection of those. So when I talk about the intersection of B and B, I'm talking about this space here, which I can see is just the 15. So I've got 15 over 320. And when I reduce that, I get 3 over 64. Last but not least, I'm talking about the probability of the union of A or C. The union talks about anything that's in A and anything that's in C. And I'm adding all of those numbers up. And when I add all of those numbers up, I get 195 over 320 as my probability. And that reduces to 39 over 64. All right. Now that's all very exciting. We can do probabilities with every single Venn diagram question I've ever given you ever in your life, which is kind of riveting. But we can also talk about probabilities in terms of our lists. We can talk about them in terms of tree diagrams. So we're blending everything together that we've learned with probability. Now, the last thing I want to talk to you about probability today is theoretical or experimental probability. Now, all of the probabilities that we have been calculating have been the theoretical probability, meaning that if everything happens ideally, like if there was no environmental impact, mathematically speaking, like this is what should happen. Now, what should happen is that the probability is found by taking the number of favorable outcomes, the number of ways that my event can occur, and divided by all of the total possible outcomes. But that's not always true in real life. So if I flipped a coin, I realize that it's a 50% chance of getting a heads and a 50% chance of getting a tails. So if I said, hey, flip a coin and you could either leave 10 minutes early from class or you stay 10 minutes behind. Whether you choose heads or tails, there's no strategy to it because there's an equal percent chance, it's equally likely that both of those events will occur. So it's just kind of random chance that you'll either call the one that it lands on or you don't. But experimentally speaking, if I actually flipped a coin and I flipped it, let's say 10 times in a row, I might find that I got 8 heads and 2 tails. That can happen. It doesn't mean that my theoretical probability is not mathematically accurate. It's just that in real life, everything comes to chance, right? There's no guarantee that what I'm saying will take place. That's why it's a probability, not a fact. Kind of like when Tim Hortons has roll up the rim. It's I can't remember what the proportion is, but they say 1 in every 6 cups wins or 1 in every 3 cups wins. I can't remember what they claim. But it doesn't mean that if I buy, let's say 1 in 3 cups, it doesn't mean that every 3rd cup I buy will be a winner. I can win back to back to back to back. Or I can lose 10 times in a row. Right? It doesn't mean for a fact it'll happen. It's just my percent chance or my likelihood of being able to get that winning cup. The thing about experimental probability, though, is that the more trials I perform, whether it be an experiment, whether it mean me flipping a coin 1,000 times, I'm going to or should get closer to that theoretical probability. So yeah, I could flip a coin 10 times and I could get 8 heads and 2 tails. But the likelihood of me flipping a coin 1,000 times and getting 800 heads and only 200 tails is less likely. The more I flip that coin, the more it's going to trend closer to the theoretical probability. So if I flip a coin 1,000 times, doesn't mean I'll get 500 heads and 500 tails. But even if I get 400 heads and 600 tails, I'm much closer to the true probability than I was when I got 8 heads and 2 tails. So the more and more I conduct that trial, the closer I will get. Okay. Well, that's it. That's all for 6.1. There's some practice that follows, so take a look at that. But for now, have a lovely rest of your day.